Hey everybody, so in this video we're going to talk about section 7.1, which is about exponential growth and decay. Okay, so first we're just going to explain what exponential growth and exponential decay look like, and then we'll do some examples. Okay, so if as x increases by the same amount, so for example, as x is increasing by 1, f of x increases by the same multiple. Okay, so in our example we said x is increasing by 1. That would mean that y or f of x is being multiplied by something. So it's not increasing by 1, but maybe it's being multiplied by 2 or multiplied by 3. Okay, then we say this function is exhibiting exponential growth. Okay, so exponential decay is as if x increases by the same amount, f of x or the y value is divided by the same amount. Okay, we call that exponential decay. So for example, as x goes up by 1, y might be halved or quartered. Okay, so let's look at an example of this. Okay, so today 6 people hear a rumor that in the fall tuition will be free. Each day the number of people who have heard this rumor triples. Let t be the number of days since the rumor started, and let n of t be the number of people who have heard the rumor. Okay, so that's our scenario. Okay, and you can see that this describes the type of function that we were talking about above, where each day, okay, so each day, for each one day, the number of people who have heard it triples. So it's being multiplied by 3 every single day. Okay? All right, so let's look at the questions that were asked about this. Okay, so part A says fill out the table. Okay, so remember t is the number of days since the rumor started, and n of t is the number of people who have heard the rumor. Okay, so if n of t is the number of days since the rumor started, or if t is the number of days since the rumor started, t being 0 means that the rumor has started today. Okay, so on the day that the rumor started, 6 people have heard the rumor. Okay, and then each day after that, the number of people who have heard it triples. So we would triple this number, so 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. Okay. 162 times 3 is 486. And then 486 times 3 is 1,458. Okay, so you can see that this is increasing really quickly, right? We're going from 6 people to almost 1,500 people in a matter of days. Okay. All right, so let's look at part B. Rewrite your answers from A as multiplication. Okay, so we're just going to make our table. Okay, 0, 1, 2, 3, 4, and 5. Okay, so this is going to be 6. Okay, then we're going to rewrite 18 as 6 times 3, right? Because that's the multiplication that we did to get this number. Okay, then to get to 54, we multiplied it again. So we had 6 times 3 times 3. Okay, then to get from 54 to 162, we multiplied by 3 again. So 6 times 3 times 3 times 3. Okay, and then again here we had 6 times 3 times 3 times 3 times 3. Okay, and then last one we multiplied by 3 one more time. 1, 2, right? 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so that's what it means by write as multiplication, is we're just writing, okay, 6, then we did 6 times 3, then we took our answer times 3, that answer times 3, etc. Okay, and then the last one says rewrite your answers from B with exponents. Okay, so we're going to make our table again. Okay, so 0, 1, 2, 3, 4, and 5. Okay, and then we're going to rewrite this with exponents. Okay, so this is just 6. This is 6 times 3 to the 1 power, right? Because there's only one of them. Then this is 6 times 3 squared, right? 3 times 3 is 3 squared. This is 6 times 3 cubed. This is 6 times 3 to the 4th. Okay, and this is 6 times 3 to the 5th. Okay, so we're just getting the exponents from how many times we're multiplying 3 by itself. Okay, now we're going to use our answers for that to write an equation for n of t. Okay, so we're going to write n of t equals, okay, so it looks like all of these are 6 times, okay, and then we have, for most of them, we have 3, okay, and then we're just going to decide what this power should be. So if you compare the exponent with the value of t, you can see that they're always the same. So this should be 6 times 3 to the t power. Okay, now how is that going to work for 0? Well, if you think about 3 to the 0 power, that's 1. So this would just be 6 times 1, or 6. So it even works for this one where it doesn't look like we have a 6, or a 3, I'm sorry. Okay, so we just got this based on this pattern here. Okay, so let's look at parts E. Okay, find n of 15 and then say what it means. Okay, so we have our equation, right? And we're just gonna plug in 15. So I'll have 6 times 3 to the 15 power. Okay, and then we're gonna use our calculator to get an answer for this, right? We think it's gonna be a super large number. So I got 86,093. 4, 4, 2. Okay, so that's the number that I get from just plugging this into a calculator. Okay, and now we're going to say what it means. So remember, when we're doing this, we're going to say what the input value means. So this is t for time, so it would be after 15 days. Okay, then we're going to say what this number means, and remember, n is the number of people who have heard the rumor. So about 86 million people have heard the rumor. Okay. All right. So now let's look at this question, which is how many people will have heard the rumor after 56 hours? Okay. So remember, t is days. T is in days. Okay. So 56 hours equals how many days? That's what we need to know first. Okay, well, 1 day is 24 hours. Okay, so we can take 56 and divide it by 24. Okay, and see that this is okay. These are both divisible by 8, so we would get 7/3. Okay, so we're looking at t equals 7/3 here. Okay, so we're going to plug into our equation. Okay, and again, we're going to go ahead and use a calculator to get an approximate value. Okay. Okay, so we would get that there's approximately 78. So after 56 hours, about 78 people have heard the rumor. Okay. All right. Now that we've done an example of this, I want to give a general form of how these exponential growth and decay functions will look. Okay. So in general, okay, these functions are going to have this form. Okay, just like we saw with the previous example where we had 6 times 3 to the t. Okay, this is going to be a times b to the t. Now a, just like we saw in the previous example, is going to be the initial amount. Okay, or the starting value. Okay, now b, okay, has 2 names. So if b is bigger than 1, like our previous example where our b value was 2, oh, I'm sorry, where our b value was 3, okay, so if it's bigger than 1, then b is the decay rate, or I'm sorry, the growth rate. Okay, it is also sometimes called the growth factor. Okay, now if b is less than 1, it has a different name. This is called the decay rate, okay, or the decay factor. Okay. The reason this is called the growth rate, whereas if it's less than 1, it's called the decay rate, is because if b is greater than 1, then like we saw in our first example, the function is going to increase over time, right? Because it's being multiplied by this number, it will increase and increase and increase. Now, if you have something where b is less than 1, right, then you have a fraction and it's going to decrease over time, right? b will be less than 1. Okay. All right. So let's look at another example. Okay. In 1999, there were 5,078 internet service providers. Analysts expected the number to double in 5 years. Okay, so this says find the annual growth factor. Okay, so what we're looking for is that value b. Okay, now the only thing that we know, it doesn't say what the annual growth factor is that it doubles in 5 years. Okay, so the reason that the growth factor isn't 2 is because that would mean it doubles every year as opposed to doubling every 5 years. Okay, so what we are going to do is say that we know the initial amount. It's given in the problem. Okay, and then after 5 years, okay, it should have doubled. Okay, or 10,156. Oops, 10,156. Okay, so let's look at what that means for us. Okay, so it means that our initial equation, okay, is going to look like 5,078 times b to the t. Okay. Now, when t is 5, right, meaning after 5 years, the output is going to be 10,156. Okay. Okay. And now, this is a power equation, which we studied in the last chapter, right? We have a variable to a numerical exponent. So we can go ahead and solve this. So we're going to divide both sides by 5,078. Okay. And then to get rid of the fifth power, we're going to use the fifth root. Okay. Now the fifth root of b to the fifth is b. Okay. And I'm just going to go ahead and write this in exponential form. Okay, so this is what it's asking for, my annual growth factor b. b is 2 to the 1/5 power. Okay. All right. So in part B, it says, write an equation for the number of providers I as a function of years since 1990, t. Okay, so we want I of t, a function. Okay, now we know that it's going to have this general form, right? We talked about that in part A. And then we're just going to fill this information in based on what we found in part A. We know that the initial amount A is 5,078. Okay, and we found in part A that B is 2 to the 1/5 power. Okay, and the only thing I'm going to do to this is multiply these two exponents to simplify. Okay. All right. That's the only question for this example. Okay. Let's look at our next example. Okay. In 1998, the average annual cost of public four-year college was $10,069, and costs were rising 6% per year. Okay. So part A says, find the annual growth factor. Okay. So for the annual growth factor here, we want to say that B is what percent of last year. Okay. Now, we know that it's going to be all of last year. Right? Plus the 6% increase. Okay. Well, how do you say all of something in terms of percent? Well, all of something in terms of percent is 100%. Okay. Plus the 6% increase. Okay. So B is going to be 106%. Okay, which we write as a decimal 1.06. Okay, 100% of last year plus the increased percent 6%. Okay, all right. Part B says write an equation for the cost C as a function of years since 1998 T. Okay, so we're going to have a function here, and it's going to have the general form A times B to the T. Okay, now A is the initial amount, so if we look back at the question, what's our initial amount in 1998? Well, it's 10,069. Okay, so we would have our A value is 10,069. Okay, And from part A, we know that B is 1.06. Okay. That's all there is to writing the equation. Once you know the general form, you just need to fill in the initial amount and the growth rate. Okay. What does your function predict as the cost now? Okay. So now we know that the year is 2020. Okay. So how many years has it been since 1998? Well, it's been 22 years. Okay, so our value for t is going to be 22 years. Okay, and we're going to plug that in for our function. So we'll have 10,069 times 1.06 to the 22 power. Okay, and then we're just going to plug this into a calculator to get our approximate value. Oops. Okay. So I get 36,284.02. Okay, so that means that our model predicts that an average annual cost, right? So the cost for 1 year of public four-year education would be $36,284.02. Okay. All right, let's look at our next example. The butterflies visiting a nature station is, the number of butterflies visiting a nature station is declining by 18% per year. In 2000, 3,600 butterflies visited the station. Okay, so this is our first example of exponential decay, and we know that already because it says it's declining, right? So it's going down, which is the same thing that decay means. Okay, so let's find the annual decay factor. Okay, so our decay factor B is going to be last year minus the decrease. Okay, so last year's amount would be 100%. Okay, and our decrease, it says in the question, is 18%. Okay, so if 18% of them are missing, how many of them are left? Well, 82%. Okay, and again, we're going to write that as a decimal, being 0.82. Okay. Now you can see this matches up with what we saw in the first example, or what we saw way earlier on where we said if b is less than 1, it's going to be exponential decay. You can see that the decay factor is less than 1. Okay. So for part B, it says write an equation for the number of butterflies visiting n as a function of the year since 2000 t. Okay, so we're going to have n of t, our function, and we know that it's an exponential function, so it's going to have this general format. Okay, let's fill in our initial amount, which if we look back at the question, the initial amount in 2000 is 3,600. Okay, and then we're going to fill in our decay factor from part A. So there's our first example of exponential decay. Let's look at another example of exponential decay. CRC's bookstore sold 984 copies of a new textbook in 2011. Each year after that, the number of copies sold is halved. Okay, so find the annual decay rate. Okay, so it says every year the number of copies is halved. So that means that the decay rate is going to be half. Okay. All right. So then it says, write an equation for B, the number of books sold as a function of T, the year since 2011. Okay, so we'll have our function. We know that it has the general outline A times B to the T, like all exponential functions. Okay, we're going to fill in our initial amount, which in the question said was 984. Okay, and then we'll fill in our value from B from part A, which was 1/2. Okay, again, you can see that when you have exponential decay, that B really is less than 1. Okay, let's look at our last example of exponential decay. An app is created on the day it's released and 5,000 people buy it. Every 3 days, the number of sales is quartered. Okay, so find the annual decay rate. Now, it's not 1/4, okay? Oh, it shouldn't say annual, it should say daily. Sorry. Okay, so it isn't 1/4 because that would say every day the number of sales is quartered. Every 3 days means that we're going to have to do some more work. Okay. So we know that we're going to have the general format A times B to the T. Okay. And we know that our initial amount is 5,000. Okay. Now the only other thing we know is that after 3 days, okay, sales are quartered. Okay, so they are 1/4 of the initial amount, 5,000. Okay, or 1,250. Okay. All right. So we're going to go ahead and plug that in. We have 1,250 equals 5,000 times B to the third, right? Because T is 3 days because it's been 3 days. Okay. Now I'm going to divide these. I'm going to get 1/4. Okay. And then to get rid of the cube, I'm going to take the cube root. Okay, now over here, this is going to be B, and over here, I'm just going to go ahead and write this in, in exponential form, so the 1/3 power, like this. Okay, so this would be my daily decay rate, 1/4 to the 1/3 power. Okay. Then it says, write an equation for F, the number of sales as a function of the days since release. So we're going to have F of T, and again, we know that it's going to be the A times B to the T format. Okay, we're going to fill in our initial amount, which was 5,000. Okay, and then we're going to fill in our value for B, which was 1/4 to the 1/3 power. Okay, and the only thing we're going to do to simplify is we have an exponent to an exponent, so we know that we need to multiply them. All right. So these really are kind of all the different types of examples that you can see of exponential growth and decay. We had one where the growth rate was just given. Every day it doubles, okay? Then we have one where some type of growth rate is given, but it's not the annual growth rate, right? Where every 3 days it doubles, okay? Then we had one with percents. Then we did the same thing with exponential decay. We gave one with descents, or one with percents, sorry. One where the decay rate is just given. It quarters every year, okay? And then this example where we know it quarters every 3 days, okay? All right, so let's look at our last example. So it says, does the table shown represent a linear function or an exponential function? Okay, and you can see that the two functions shown here are pretty similar. Okay, in fact, they have the same first 2 points. Okay, so we're looking at as x is increasing by 1, what's happening to the y value? Okay, so here you can see as x increases by 1, the y value is being halved, right? Half, 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 half. Okay, this is a perfect example of exponential decay. Okay, now let's look at this example. So again, x is going up by 1. Now you can see that the y value is going down by 50. Minus 50, minus 50, minus 50, minus 50, right? This is the perfect example of a linear function. Okay, and way back in chapters 1 and 2, when we talked about linear functions, we talked about this. The change in y and the change in x between every pair of points should be the same. So as x goes up by 1, y goes down by 50 for each point. Okay, let's look at our second two functions. Okay, again, you can see they have the first two same points, right? 0, 2, and then 1, 6. Okay, again, x is going up by 1 each time. So let's see what's happening to our y values. Okay, so as x goes up by 1, here we're getting either times 3 or plus 4. Okay, so here you can see that you really are adding 4 every time. So as x is going up by 1, y is going up by 4. This is a linear function. Okay, again, you can see that the slope between each of the points is the same because the change in y is 4 and the change in x is always 1. Okay, let's look at this. Here we can see that as x is going up by 1, y is getting multiplied by 3. Okay, this is the perfect example of exponential growth. Okay, so as x is increased by a fixed amount, here 1, we can see that the y values are multiplied by 3. Not like here where you're adding the same number every time, that makes it linear. Here you are multiplying by the same thing every time, that makes it exponential. Okay, all right. I hope that you guys will practice some of these word problems in the homework. They can be tricky, but like I said, there's not too many different types of examples. There's really only 6. So I hope you practice them, and I will see you guys soon.